Hello class, welcome to lecture 17. Today we're talking about confidence intervals. And so it's sort of like the opposite of what we've been doing. So let me remind you what we did last time. So last time we looked at populations with some proportion. So we studied sample proportions. So there was some proportion of the population that you call P, having some property or trait. So that's how the problem begins. Then there's a normal distribution that you create from that information, and based on the size of the samples that you take, where this is the mean and the standard deviation is called sigma. So you add that amount to get to the right hand inflection point, and you subtract that amount to get to the left hand inflection point. And this mean is secretly just the proportion that you're given at the start, and the standard deviation is a little bit more complicated than that. You have to do the proportion times 1 minus the proportion and divide that by n, and then square root that. So then, using this distribution, you answer questions about samples. So that was the big idea last time. But now, so what's wrong with what we did last time? Well, we're sort of doing something not that helpful yet, because what we're doing before is we already know the population proportion, and we're just looking at samples. But realistically, you don't know this. You don't know this already before you do the samples. You do the samples first. So now we do the reverse. So meaning we want to estimate the population proportion using samples instead of talking about samples when we already know the population proportion. Okay, so we want to estimate the population proportion P based on a sample proportion. So it's a specific sample proportion, so we call it little p hat. Okay, so this is the idea. Let's put it into the context of a problem. So for example, we could take a sample of Whittier College students, and let's say we take 100, size 100, and let's say that 70 of them have watched the show The Office. So I'm just making up these numbers, but let's just say that this is what's happening. Well, then what's going on is I don't know the actual proportion of Whittier College students that have watched The Office, but I have a sample proportion of 70 over 100 of them. So 70% of this sample watch The Office, have watched The Office. So then the question is, how do we know if this, I'm going to call it the fancy word that the stats people use. This is called a point estimate. How do we know if this point estimate is a good or bad estimate? How close is it of the actual proportion of the population, which in this case would be Whittier College students that have watched The Office. So that's what we want to talk about today. Try to answer this type of thing. So it's going to be very theory heavy. We have to use some cool math to figure this out, to figure out how to think about this stuff. And then in the next lecture, we will do more example-y stuff. So hopefully the examples always convince you that the theory is not as bad as it first seems. Okay, so on to the cool math. So there's our sample proportion that we found, 0.7. And there's this normal distribution that we can still look at. But we don't know anything about it this time because we don't know the actual proportion. So the middle of this distribution is still this thing. But in previous problems, you would say, oh, well, that's just whatever the given proportion is. But now I don't know what that is. But our 0.7 is somewhere on here. I don't know where. It could be maybe 0.7 is there, maybe 0.7 is over there, maybe it's over here, maybe it's very close to the middle. It could be anywhere. We don't know because we don't know what this is. So that's the idea. So we can't know for sure where p hat is, but we can still do some other stuff. The only way to know exactly where p hat is to know exactly where p is, but that would require knowing the exact population proportion, which would require asking all the Whittier College students and getting that information. So can't do that, but we can find some other useful information. Okay, so to do this, we use properties of the normal distribution. So properties of this thing that I just drew. Okay, so for example, what's a nice property of this? 95%, because it's a normal distribution, 95% of the area is between these two z-scores. And that's just because it's a normal distribution. So why 95? Well, this is just a commonly used number, but we can change this. People just like 95 for some reason. But that would also change these too. But the point is, if you go and you look at your little z-score calculator, what's going on is that the z-score between, sorry, the area between these two z-scores is 95.95. So how can we take advantage of this? Well, what that means is that if you take a sample proportion, if you get a p hat, 95% of them are between these two z-scores. That's the idea. So 0.95 of the possible sample proportions, p hat, are between, well, I got to translate my z-scores into actual data points on this distribution. So what are these two data points? Well, this is p, this is the mean, plus that many standard deviations. And whatever your standard deviation is, which we don't know yet either. And this is p minus that many standard deviations. Because remember, z-scores are just amounts of standard deviations. So 95% of the possible sample proportions that you could get, if you take a sample proportion, are between these two numbers here. They are between 1.96 standard deviations from the middle. And that's again because 95% of the area is between those two things. It's probably a little bit wider actually, but whatever. So just a drawing. It's probably about there maybe. Okay, good. So then, what does this mean for us? This means that for 95% of the point estimates that you could get, of the sample proportions that you might get by taking a sample, that you could say that, well, how do math people say between? We're gonna say between in a fancier way. Between just means that it's greater than the left one and it's less than the right one. So this is really what we're saying when we say that it's between these two numbers. But then with some algebra that you may or may not remember, you could solve for the proportion being in the middle instead of the sample proportion. So what this is telling us is that although I don't know exactly where the real proportion is, I can be pretty confident that it's between these two numbers. So which means that for 95% of the sample of the possible sample proportions, that you could get, that the actual proportion P that we're looking for is between these two numbers, is between this and this. So your point estimate minus 1.96 standard deviations and plus 1.96 standard deviations. Okay, so the idea, what we're going to do is not going to be so theory heavy, so don't worry too much. But the idea is that our sample has an interval around it. And in this context, our sample is going to always be called a point estimate, because it's like the initial estimate of the actual proportion. So it has an interval around it, and that also will have a special name called a confidence interval. Stats people just like to add on extra fancy names to confuse everybody. But the idea behind the confidence interval is that you can be reasonably confident that the actual proportion is in there. So that's, I guess, why they picked that name. So you can be reasonably confident that the true proportion is in there. Sorry, so the idea that, I skipped a bunch of words. So the idea is that our point estimate has an interval around it called a confidence interval, where we can be reasonably confident that the true proportion is in there, I guess. Is that a sentence? Okay. So how confident can you be that it's in there? Well, it's actually a precise question. It's not a, I'm sort of confident, not really. It actually has a number we can associate to it. How confident can you be that the actual proportion is in this confidence interval that you're creating? Well, this corresponds to the initial choice that we made about how big of an area we want to cover. So this corresponds to the amount of area you're covering. So we picked 95% of the area, so our confidence will correspond to 95, and I'll say how to say it in a second. And this confidence level, it's called the confidence level, the amount that you're confident. But again, the confidence level just corresponds to an area, really, or a probability. So in this case, we would say that we are 95% confident. And it's not just like we're estimating our idea of confidence more abstractly or something. It's literally just based on this number that we picked initially. So we say that we are 95% confident because our original area that we chose was 0.95. So if I chose a different area, then I would have a different level of confidence. So that's one thing to notice. So we can increase the initial area if we want. So it seems like a good idea first, because of course you want to be more confident. So maybe I'll increase it to say 0.99, but it'll have a drawback. So this will make the confidence interval wider. But what's wrong with that? What's wrong with making a wider confidence interval? Well, this means that you're less precise about where you think the proportion actually is. And so that's the drawback. So it creates a less precise guess that we can be more confident about. But so now we can be 99% confident about. We could say that we're 99% confident that it contains the true proportion. So why is that? Well, this is because, so why does it get wider? It's because now the 0.99 area is between two different z-scores, which are further apart. So negative 2.58 and 2.58. That'll contain 99% of the area. And so the confidence interval will be wider for that reason. But it all works out the same. So all we're doing is we're still looking at the distribution where we don't really know where the true proportion is, but we know that if I add 2.58 and subtract 2.58 standard deviations, that I'll get 0.99 of the area. And then going through the same argument as before, I'll get the same idea as I did before with the where I said that the true proportion was between these two things with 95% confidence, but now I'll say it with 99% confidence. So it all works the same. So this results in 0.99 of the sample proportions that you could get, p hat, being between these two things. Oops, sorry, this one's a minus because I'm subtracting. Being between these two things. .58 standard deviations. So then, following the same logic as before, we are now 99% confident that the true proportion of the population that you're studying, P, the true proportion P, is between, now we use that same algebra as before, between our point estimate minus 2.58 instead of 1.96 standard deviations, and our point estimate plus that amount. So we're more confident, but we're less narrowed down. And that's the trade-off. So of course you could be 100% confident if you went infinitely out to the left and to the right, but that wouldn't help you at all. That would just be saying, I'm 100% confident that my proportion is a number. And that doesn't tell you anything. Just because you know it's a number doesn't help you. So you have to trade off some confidence for narrowing down your guess, is the idea. So you can go the other way. So similarly, you can narrow it down, but be less confident in our estimate, in our interval. So the other often used number is 0.9. So if we lower the confidence level to 90%, then what we're saying is we're doing all the same stuff, but now we're looking at the z-scores that will tell us the middle 90% of the area, 0.9 of the area. And the two z-scores that do that for us are negative 1.64, and it's always symmetric, so 1.64 will be the other one, which means that the area here is between 1.64 standard deviations on either side, and then we do all the same stuff. So then we can be 90% confident, so less confident, but more a smaller interval, so more precise of a guess. So we can be 90% confident that P is between our estimate minus 1.64 standard deviations and our estimate plus 1.64 standard deviations. Okay, so in the next video, we will go through an example of how to use this stuff. This is all the theory. Okay, so see you next time.